like, share, subscribe.
Hey y'all, welcome back. Tonight's homework consists of variations on the same 5 problems that we talked about in class. There's no multiple choice here, but I think we can still handle it. We're going to solve these very similar to how we did the ones in class. And so let's just get started with number 1. It says rearrange the expressions in order from least to greatest. So we need to know exactly how big each of these numbers are, and I don't think it's super obvious just by looking at the exponents. You can definitely try to simplify each of these using exponent properties, writing them all in terms of base 2, except for maybe this one over here with the base 3. But honestly, I think the easiest way to answer a question like this is to pull out your calculator, which I'll do right now, and just type each one of these in and keep track of how the value of each one of these. So let's just go ahead and type the first one in. We've got 4 to the power of 2 cubed. And I would recommend, just to make sure that there's nothing going wrong with how you're typing this in, I would recommend you type this in exactly how it looks on the paper. So that way you don't have any issues with dealing with parentheses or anything like that. So we have 4 to the power of 2 cubed. I'm going to go ahead and hit enter, and we can see that this is 65,536. So I'm just going to write that down just to keep track of it. Let's see here. There we go. So this is going to equal, there we go. What did I say it was? 65,536. Okay, so that's the value of the first one. Now we'll do number 2, which is 4 squared and then cubed. Okay, so let's see what this is. 4, well, let's get those parentheses. 4 squared cubed. All right, 4,096, a little smaller than the last one. So far, this is our smallest one yet. Let's do the next one. 2 to the 4th power cubed. So parentheses here, just want to make sure it looks exactly like I see it on the paper so there's no mistake in how I'm typing it in. 2 to the 4th power, we're going to cube that. Wow, look at that. That was highly unexpected. It's exact same number here. Is that right? Oh, I guess, you know what? 4 squared is the same as 2 to the 4th, so that doesn't surprise me. Now, in terms of ordering these, don't worry too much about it. As long as these two are next to each other, you'll be okay. 2 to the power of 4 cubed. So let's type this in. 2 to the power of 4 cubed. There we go. Whoa, what is going on with this number? We've got 1.84, a bunch of decimals, and an e to the 19. So you got to be on the lookout for this. This whole e to the 19 is the calculator's way of communicating scientific notation. And so basically what this means is about 1.8 times 10 to the 19. 1.8 times 10 to the 19th power. In other words, really what this is, and I'm just going to, I'll write it up here briefly, but I'm going to take it down just because it's sort of unnecessary. But when you have 10 to the 19th as your multiplier here, this is going to be a huge number, because basically what this is going to be start with that 1, and then we have to have 19 digits before we hit the decimal. So I'll just type this in, 84467, 4407. So far, I've only accounted for 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. We got 10 more, so we'll just throw zeros in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as you can see, this is a just ginormous number, way bigger than the other two, and so that's why when you have these huge numbers, it's a lot easier to write it as scientific notation. Now, I don't know whoever programmed this, what the deal with the E, like why they couldn't just write times 10 to the 19th. I don't know. You'll have to ask Texas Instruments on that one, what the purpose of that weird notation is. But at any rate, this is going to be what this one equals. So far, this is by far the biggest one. So let's try the next one, which is going to be 3 to the 4th. Oh, forgot my parentheses. So 3 to the 4th, and then that number squared. 3 to the 4th, that's going to be 81. So 81 squared is not going to be that big. 6,561. So let's go ahead and write that down. 6,561. And so now we can put everything in order. So let's look for our smallest one. Smallest one's going to be either one of these two, so don't worry too much about the ordering on these two. They're both going to be equally small, so you could just kind of put them in any order you want here. So let's start with the first one, 4 squared cubed. Put that first. I guess you can't see what I'm putting here, so I'm going to hide my calculator since I'm done with it. There we go. So we got 4 squared cubed, and then the next one should be 2 to the 4th cubed. Again, both of these are equal, so the order here doesn't really matter since they are the same. But now the order is going to start to matter here. So the next biggest number is going to be this one over here, the 6001, and that is 3, if I can type. It's not going to let me type. There we go. 3 to the 4th squared. And then we've got this 65,000 number. That's this one over here. The 4 raised to the power of 2 cubed, which is really just 8. So this is really just 4 to the 8th power. Still a pretty big number in its own right. But this one over here, oh my goodness, this is like by far the biggest number. It's not even close. Like these are not even in the same ballpark. 2 to the power of 4 cubed. Okay, so there you go. Now we've rearranged these expressions in order from least to greatest. We did happen to have 2 that were the same here, so the order there is not really that important since they are equal. But the rest, these last 3, should definitely be in this order. Number 2, it says simplify the expressions. Now here, we just have to know and be able to use our exponent properties. And really the 2 key properties that you need for these are the product property, which states that if you've got 2 powers that are being multiplied, if they have the same base, we can combine them by adding the exponents. So we'll take advantage of this property. And then we also have to deal with negative exponents. So it's important to know that whenever you have a negative exponent, then that is equal to 1 over that same base with the positive exponent. So these are the kind of the 2 key properties to be familiar with to get these right. So I'm gonna box these just so that we can refer back to them later if we need to, but we'll need both of these for number 2. So 2a, we've got this expression here. What I would do first is just rearrange these terms to make it a little easier to look at. This a doesn't have an exponent on there, and what I'm going to do just to make this a little easier is write it as an exponent of 1 times a to the power of negative 4/5. And now I'm going to write my b's. Multiplication is what we call commutative, which basically means that the order doesn't matter. You can rearrange any factors in a product and you should get the same answer. And a simple example of this would be like 2 times 3 is the same as 3 times 2. And so that's what allows me to rearrange these terms in any order I see fit. And so here we go. I put the 1 here just to remind you that if you don't see an exponent, there is an implied 1. But now we can combine these. So we're basically going to combine the a's and the b's separately using this property up here. So we're going to add the exponents together. So here we have a to the power of 1 plus a negative 4/5. So yeah, plus a negative here. It's probably easier to just say minus. And then times b, and then we'll combine these two, so we need to add these two together. 3/5 plus 2/5. And so now we'll simplify each one of these. So 1 minus 4/5. Now 1 is the same thing as 5/5. So 5/5 minus 4/5 is 1/5. And then 3/5 plus 2/5 is 5/5, and 5/5 reduces to 1, and we don't technically need this 1 here, so we're just going to leave it as a to the 1/5 times b. Do not need an exponent here, because if you do not write an exponent, it is assumed to be 1 anyway. So that's my answer for number 2. Or number 2A. Number 2B is a very similar problem. It's the same kind of idea. We do want to rearrange these a little bit, so let's start with that. We've got x to the negative third times x to the 3/4 times y to the 1/3 times y cubed. So now I'm going to use this property over here to combine the like variables. So I've got negative 3 plus 3/4 to put together those x's. And for the y's, I've got 1/3 plus 3. So we'll have to do a little arithmetic with fractions here. Hopefully you can handle that. So this one's going to be x to the power of, now here, let me just copy and paste this here for a second. Here we've got negative 3 plus 3/4. Now 3 times 4 is 12, so negative 3 is equivalent to saying negative 12/4, because 12 divided by 4 is 3. Now we've got a common denominator here, and so we can combine those. So we've got negative 12 plus 3 is going to be negative 9/4. For the y's, we need a common denominator here too. 3 times 3 is 9, so we can rewrite 3 as 9/3, and we can add those together. So we get y to the power of 1 plus 9 is 10, so we get 10/3. The last thing to do is try to rewrite this without a negative exponent. And so we can do that by simply not really changing much, but just rewriting this so that this term right here, this x term, is in the denominator of a fraction, and that will allow us to change this to positive. Basically, we're going to take advantage of this negative power property. So our final answer here is going to be y to the power of 10 over 3, all of that divided by x to the power of positive 9/4, and you could just leave your answer like that. All right, that's number 2. Number 3 says a colony of bacteria starts with 4 bacteria at noon. If the colony of bacteria doubles every 30 minutes, how many bacteria will be present at 3 p.m.? So let's start to write an equation. We'll say the final amount, we'll just call that y, is equal to the initial amount, which we started with 4, times the rate. Now if it doubles, that means we need to multiply by 2. And so let's count and see how many times do we need to double. If it's noon, and we want to know, well, how many bacteria are present at 3 p.m., from noon to 3 p.m., that's 3 hours. But if the bacteria doubles every 30 minutes instead of every hour, that means we'll have not 3 doublings, but actually 6. So we're going to put a 6 up here in the exponent. And then this is something you would just put in the calculator. And so I'm doing that over here. 4 times 2 to the 6th is going to give us 256. Okay, that's our answer for 3A. 3B is pretty much the same problem here, except it says how many would be present if the colony tripled instead of doubled. So really the only difference here is that instead of having a 2 for the doubling, we're going to change that to 3. There's still going to be a total of 6 doublings because they're happening every 30 minutes. So we'll type this into the calculator just like we did the last one. 4 times 3 to the 6th power. By the way, it's not 256. I just haven't erased it yet. 2,916. So yeah, quite a bit more. All right, number 4 says solve the equations for x. Now we did one of these in class, and these problems will be worked very similarly. The idea here is that as long as we can write both sides of the equation with the same base, we can use the one-to-one property we went over in the, well, actually that was 2 units ago, back in Unit 7. But you can use that one-to-one property to drop the bases. So yeah, 16 can be written as 4 squared. And now that we have the two bases equal, we can set the exponents equal to each other, 3x equals 2, and just solve this like a normal linear equation. Divide both sides by 3, and I get x equals 2/3. 4b is very similar, except here we're trying to write both sides of the equation as a base of 3. So we got 3 to the power of 2x equals 3 cubed, which is 27. 3 times 3 is 9, and if you multiply 3 one more time, that's 27. So now that we have the bases the same, we can solve this basically the same way we did a, which is to say we need to set the exponents equal to each other and then solve. Dividing both sides by 2, we get 3 halves. Part C, again, this is basically the same problem as 4a, just with a base of 3 instead of a base of 4. So here you have 3 to the 3x equals 3 squared, because 3 squared is 9. Here, and then we can set the exponents equal to each other, 3x equals 2. And so now you can see why we're going to get the same answer as 4a. Dividing both sides by 3 gives us 2/3. And that's number 4. So that leaves us with one last question here. Number 5 says the population of a certain city was 10,400 on January 1st, 2013. If the population increases by 9%, okay, so that's going to be our rate. Right here, here's our initial amount. Maybe I'll make some notes here as we go along. So yeah, this is our initial amount. The 9%, that's our rate, but remember, when we write the rate, it's actually 0.09. We've got to write that as a decimal. Okay, it says the increases by 9% for the next 3 years. Okay, so this next 3 years, that's going to be our t. So our t value is 3. Write an equation to approximate the population of the city on January 1st, 2016, which is 3 years from here. They already kind of spelled out the t value here, so we don't really care about that. So let's go ahead and set up our equation here. To set up an exponential growth equation, and I'll write that here just so you can kind of go back and review your exponential growth notes. The setup for an equation like this looks like this. Y equals my initial amount, which I'll call A, times 1 plus the rate of growth raised to the power of the number of years, which would be t. All right, so the initial amount, like we said, is 10,400. The rate is 9%, so this should be 0.09. And then the time is 3 years. This is something that you could just put into the calculator. If you want to simplify things just a bit before you do that, you can add these together to just get 1.09. It's a little cleaner that way. But yeah, at the end of the day, you're just going to be putting all this stuff in the calculator. So I'm going to move this up just to get a little more room to write my final answer here. And then I'm going to jump over to the calculator. And I'm typing in 10,400. Oh, forgot a 0 there. Oh wait, you can't see what I'm doing. That's okay. I'm just typing this in sort of behind the scenes. Times 1.09 to the power of 3. And that gives us approximately get that little approximate symbol going here. And I'm getting 13,468. 13,468 people. Now you do get a decimal in there, but because we're talking about numbers of people, you want to round to the nearest person. Can't have like a half a person or anything like that. You can't have a fractional person. So yeah, that's our answer for number 5. And that about wraps it up for tonight's homework. As always, please reach out if you have any questions. And otherwise, you'll have a great day, and I'll see you next time.